Hello everyone. So in this video, we'll talk about the paper Attention is All You Need by Google, right? Google Research, Google Brain. It's a little bit of time that this paper was released, and everybody know about this, right? It has led to the famous transformer architecture. Um, so um, you know, so there are a lot of content in YouTube talking about attention, what attention is, a lot of resources to get to know what attention is all about. Um, but I thought maybe it's time to, maybe there is a need to go dig into the paper, right? And see what we can get, right? What we can understand from the paper. So let's try to understand the paper here. So let's jump into the abstract, right? So what they are saying here is that um, one of the dominant sequence transduction models where complex recurrence, right? So RNNs or convolution neural networks, right? With encoder and decoder apart. So these were the kind of models that we had. Um, and also, some of the best performing models had attention, right, with recurrence or CNNs. So, but in this particular paper, what they're doing is they are just getting rid of the recurrence and convolution neural networks, right? All that just by solely by attention mechanism. They are trying to build an architecture which is able to perform well on various tasks like machine learning, machine translation tasks, right? And here they are reporting two tasks, so English to German translation task with this particular translation score of 28.4, and also English to French translation task with a score of 41.8. Right. So I'll talk about this particular scoring mechanism later on, right, in detail. But just know that this is used to assess how well your model is able to do these kind of translation tasks, right? So going into the introduction, we see that so RNNs, LSTMs, gated recurrent neural networks have been the state of the art in sequence modeling and transduction problems, right? Um, and and various efforts have been made to push the boundaries of recurrent language models and encoder decoder architectures, right? So they have these papers here. Okay, so let's think about RNNs, right? So what exactly an RNN is. And let's say you have an encoder and a decoder part, right? So we are trying to build a model for, so this is encoder, this is a decoder. So we are trying to build a model for, let's say, generating new output, right? So let's say kind of language translation or something like that, right? So you have an encoder part. So what happens here is it takes an input from hidden state ht minus one. It takes an input at time t xt, right? And then it will produce a new output ht, right? This is a new hidden state which will be passed on to the next RNN head, and it will take a new input xt plus 1, and then it will produce a new output ht plus 1, which will be passed on to the next one, and there will be next token here, uh, and so on, right? So, and then there's a connection to the decoder part. In the decoder part, what can happen is there's a head, right? It's again RNNs, right? It's all RNNs, but what can happen here is, let's say you're generating new output. So let's say you start off with the start token, right? Uh, let's say this is the start token. I'm just giving it some random name, and then it will produce an output which can be used. So let's say this is decoder, which can be used and used as an input for the next RNN, right? And which can be further used to produce. So the output from this one is used for the next one, and so on, right? And this is how you produce new outputs, right? And also you have connections here. So there's hidden state, which is being passed on from the previous one to the next one. Okay, so this is how you the models were. So very simple one, right? Using RNNs, encoder and decoder. And on top of that, you can also have attention that is, you know, a mechanism to just, which can just attend over all these hidden states in the encoder part, right? And then there's some mathematical way of doing it. And you can have a context vector which can be passed on to your decoder part, and which can be used on top of the hidden state and the input from the previous RNN, right, to produce a new one. So in this way, you can have long-term dependencies, right? So this kind of models are possible, right? And it's there with RNNs, but it has recurrence, right? So again, the issue here is you're passing input tokens one step at a time, right? So you're passing the token xt, and then you have to wait for it to produce the hidden state, and then you can pass the next one, and then you can pass the next one. So there's this recurrence that is happening here. So parallelization is not possible, right? You need to wait for all the tokens to be passed before you can have an output from this one, right? And yeah, so again, these were the kind of models that we had, right? And you also had CNN models. But what's happening in this paper is they are trying to get rid of this recurrence, right? And only have attention, right? So we'll see how this is done in the paper, right? Right. So this is the model with recurrence, right? But here in this paper, what they are saying is instead of this RNNs, they just got rid of RNNs, right? Instead, now you can pass all the input tokens at one time, right? So rather than waiting step by step, like time one, time two, time three, you can just pass everything, right? The whole sentence in one shot. So the entire sentence is just going to be passed in one shot to the model, right? Which will have an encoder decoder, right? Which will have an encoder and a decoder, and there's a connection, and it will just try to produce the output, right? So we'll see look at the details, right? So, but this is what is going to happen later as we move down, right? So, okay, so so that's what they are mentioning here. Attention mechanism have become an integral part of compelling sequence modeling and transduction models in various tasks, right? Allowing modeling of dependencies without regard to their distance in input and output sequences, right? So that's exactly what I mentioned here. Now, so with transformer, you can have more parallelization and can reach a state of the art in translation quality, right? With very little training hours, right? So so they claim that the training duration was quite small, right? And yeah, so let's go down. So what they discuss here is that there are many, you know, so many models, convolution neural network models, like all these, right? S2S, ByteNet, and extended neural GPUs, right? They have this CNNs as the basic building block, right? But the thing is, here in these models, the number of operations required to relate signals from two arbitrary inputs and output positions grow in distance between them. So that means to have any relationship between the input token and the output tokens, let's say, right? it depends on the distance, uh, or the number of operations, right, uh, required to relate these two will grow depending on the distance between them, right? And that's bad, right? It makes it more difficult to learn these long-term dependencies between these positions, right? But the transformer model that we are going to discuss is going to just get rid of this, right? Um, and it will have just a constant number of operations, right? Just a constant number of operations between any given input and any given output, right? And we'll see that. But they say that this is at a cost of reduced effective resolution due to averaging attention weighted position. So we'll try to look into this later, but for now this is good. Um, okay, now let's go down. So let's discuss the model, right? So what's the model architecture? So everything is here in this diagram. This is the entire architecture. So as you can see, there's an encoder part and a decoder part, right? And a lot of things are going on, but we can dissect it. We can try to understand what this entire thing is. Okay, so let's start with the inputs. Now, again, as you can see here, there's an encoder, there's a decoder, right? And in the encoder, you need to pass your inputs. In the decoder part, you will have to pass your output token. So you basically start with the start token, right? So if you want to generate new outputs, right, you first start with the start token, right? Uh, I mean, this is a weird way of writing the start token, but anyway, um, so this is start token that you will pass into the decoder part, and then it will output probabilities, right? So these of what is a possible next sentence, right? Or what is a possible next token? I'm sorry, not sentence, the token. Right. So first step, right, is as you can see here, there's embedding. So input embedding, output embedding, and then there's also this positional encoding, right? So you need positional encoding because you're passing your entire sentence or sentences in one shot, right? So um, there's no passing the token one time after the another. Just like how we saw in RNNs, we are not passing it one step at a time, right? We are passing the entire thing, right? All your sentences, right? All your sentences in one shot. So everything goes in to the input embedding, right? And so it needs to keep track of those tokens, right? The order in which the token was passed, right? Or basically positional encoding, right? And the way they do this in the paper is through some trigonometric functions, right? So they use sine and cosine functions to build this positional encoding. So what do I exactly mean by that, right? So I'll show you the function later on, but first let's understand this embedding part, right? So let's say your sentences, it will be broken down into tokens, and every token, right? Every token will be embedded in this input embedding to a vector of dimensions, let's say 512, as mentioned in the paper. D model is 512. So the token will be embedded in a vector of dimension 512. Now, when you do positional encoding for this vector, right? So it's basically assigning a positional information, right, to this token. So again, it will have it will produce a vector of same dimension, so d 512, right? A vector of length 512, and then you add it up, right? And then you add it up. That's exactly what's happening here. So you add these two, and then it's getting passed on to the model. It's getting passed on to the encoder model, right? Sorry, the encoder part of this model, which is the transformer, right? So this is what happens in this particular stage here, right? So let's erase all this. So we have the token, its input embedding, the positional encoding, and then it gets passed on to the encoder part. Now, as you can see here, the first step is the attention, right? And what exactly it is, right? But even if before going there, you can see there's three. So we gave in one uh, input, right? And it has this three inputs which is being passed on to attention. So what's going on here is that I'm going to name them Q, K, and V, right? Query, key, and values, right? So let's understand what query, key, and values are, right? So based on whatever be the input uh, embeddings, right, for all the sentences, what's going to happen here is that there will be a query, key, and a value matrix being created from these input embeddings, right? So from these embedding, I'm sorry, with both of them, right? So positional and encoding. So whatever be the input that you pass here, so you will create, these query, key, and value matrices. And the way it is being done is by multiplying with some matrix, right? So WQ, WK, WV, right? So whatever is the input, and by multiplying it with the weight matrices, you will produce these query, key, and value matrices, right? And what exactly is this query, key, and values, right? So to understand this, what I'm going to do is I'm just going to give you an example through a sentence, right? So let's say, so the man was wearing a blue shirt, right? If this is the sentence, right? And let's say, you know, um, here what's going to happen is it's trying to figure out what are the relationships between words, right? So for example, when we read the sentence, we can understand that the man was wearing a blue shirt. So there is some link, or these words, right, are not just individual tokens alone, right? So there is a kind of link or association with all the other words, right? And what's happening exactly is that here it's trying to form those associations, right? It's just trying to build those kind of associations with other words in the sentence, right? It's just going to do a self attention, right? And what kind of an attention it will do? So there's as I told you, there's a query, key, and value matrices, right? So as you can see, it's a query, and these are the keys and these are the values. So it's a kind of query, like it's asking, maybe I'm just cooking this up. Let's say, what is the man doing, right? If that's a query, right? Let's say if that's a query, then the answer is, well, he's actually wearing something, right? It's not. There's no action happening here. It's just that he has a blue shirt on him, right? So blue and shirt, right? So maybe for this query, these two words are closer, or the embeddings of these two words are closer to this query, right? And so it's trying to build a connection between other words, right? So this is a very naive, or a rudimentary way of understanding what's going on in uh, query, key, and value. And the reason why I said that is because the Q, K, and V, right? It's just it's determined by the model, right? So it will learn what these Q, K, and V matrices are based on the training that it has gone through. And so when we do back propagation and things like that, it will adjust the weights of the matrices, and hence the Q, K, and V matrices, right? So it will learn. So it's difficult to understand what exactly is happening inside the attention, right? Exactly what kind of relationships that it is trying to form and all that, those questions cannot be really answered. But just to give you a sense of uh, what is the meaning of query keys and all that is why I mentioned this, right? So there's a query, and there will be keys, right? Corresponding keys corresponding to all these words. So the man was, right, wearing blue shirt, right? So these are the keys, and the query and the keys, you're trying to find the similarity, right? And so, and then you will find the best ones, right? The most closer embeddings. Okay. Um, and I will talk about the value matrix again. Um, okay. So, right. So, as I said before, it's trying to find the relationship between, or it's trying to find connections between the words or embeddings. Now, the way they do it, right? The way this whole thing is done is by a math function. You can say it's a math function. It's nothing but the softmax of q k transpose divided by square root of dk and then b. So this is the attention, right? It's exactly what is mentioned in the paper, right? So if we scroll down, if you try to scroll down and let's have a look at it. Right. So this is the attention, right? Attention query key and values. It's the softmax q k transpose divided by square root of dk v, right? So what's all this, right? So if we go up, so they are using a dot product, scalar dot product attention. There are other attention mechanisms, but they are using the dot product one because they tested it. They tested the other one as well, and I think what they mentioned in the paper is that this one is the best. It's going to do the best when you choose this attention mechanism. So you have the softmax, you have this. So what's going on here, right? So let's look at this QK transpose, right? This particular matrix. So as I said, depending on your input sentences, right? Depending on your input sentences, there will be queries and keys, right? So let's say there is Q1, Q2, etc., Qn queries, right? There are n queries which has been created depending on the inputs, right? So the number of tokens that you have, right, in the input, depending on that, you will have Q1 to Qn, right? And then the Q1, each and every Q1 is of length 512, right? So that should be clear. So Q1, the length is 512, and the reason being it's all embeddings, right? Whose length is 512. So Q1, Q2, everything will have a length of 5. So actually, I realized that that's not correct. The reason being, it's not exactly 512. So when you multiply with this matrix W, so what exactly happens is when you have this matrix W, right, it's going to give you this query vector, right, which will be of different. So each and every queries will be of different lengths. So what do I mean by that? So they are actually reducing the dimension. So it's not exactly 512. They have this query vector of length dq, right? Every one of them will have a length of dq, right? And then every one of the key matrix, right? So they are taking a transpose of this, so that this will be K1 transpose, K2 transpose, Kn transpose, right? Every one of them will have a length of dk, right? And the reason being they have kind of like split 512 into these smaller dimensions, right? So the smaller dimensions. So this is So in the paper, dq and dk happens to be 64 dimensional length, right? And they have splitted it up into smaller vectors, and then multiple attention happens. So multiple attention heads, or these softmax functions, happen parallelly, right? So that you can understand then that instead of looking at 512 length, they have chunked it into smaller ones, but multiple heads happen simultaneously. Um, and okay, so the length is not exactly 512, it's 64, right? And but let's look at this. So what exactly is softmax qk transpose divided by square root of dk? So if you look at qk transpose, this is exactly the dot product, right? So q1 k1 transpose. So you multiply this row vector with this column vector, and then next one will be q1 k2 transpose, right? And so on till q1 kn transpose, right? So you take the dot product, q2 k1 transpose, q2 k2 transpose, etc., q2 kn transpose, right? So last one will be qn k1 transpose. So you're basically doing a dot product, qn k2 transpose, etc., qn kn transpose, right? So as you can see here, you're just taking a dot product of query and keys. So it will figure out which two vectors are close together, right? So they are of the same length, query and keys. Which two are the same, close together, right? Depending on the dot product, right? So if two vectors are close to each other, their dot product is going to be larger compared to, let's say, a vector which has a larger angle, let's say 90 degrees, or a greater than 90 degree, right? If it's larger than that, then your dot product is going to be negative, right? So so dot product will just tell you how close these two vectors are, right? And it's going to give you this resultant matrix here. Now what's happening here is, as you can see here, the square root of dk, square root of dk, which is being multiplied. And the reason being, when you take this dot product, and this happens many times. So as you can see here, this is happening nx times, right? N being 6. So this is happening many times. So as mentioned in the paper, they suspect that this dot product is just going to blow up at some point, right? And when you take softmax on top of it, right? So softmax is nothing but if you have a vector of length, let's say this is your vector. When you do softmax, what's happening is you are producing a new vector of this normalized vector, right? This one, right? This is the normalized vector that you get after you do softmax, right? So it's e to the power z1 divided by sum of all the e to the power of zi's, right? So you're taking the exponential and then you're summing it up, all of them. On top of that, it's just exponential of z1. Here it's exponential of z2. So this is the softmax, right? So you can see it's a normalization process that's happening here. So when you do softmax, if the number blows up, right? If the number blows up, then this softmax can become extremely large, right? So so things like that. So there can be some issues with this, right? So you can run into such troubles. So you just divide it by the square root of dk, which is the dimension of the vector, right? So this is exactly what's mentioned in the paper, right? So they divide by square root of dk, and okay, so you have this. Now you take the softmax of this entire thing, right? Softmax of entire thing. So So what's happening here is when you take the softmax of a matrix, what they mean is you take the softmax of every row, right? So you take the softmax of this one, then softmax of this one. So you're basically normalizing the rows, right? You're normalizing the rows. And that's exactly the softmax is. So softmax here means you just normalize the rows for a matrix. When you do it on a matrix, right? A matrix, this is what happens. Okay, so that's exactly what happens in this process. Now at the end, you can see what's going to happen is you're just going to multiply it with vector or the matrix V. Again, matrix V is created with by using this matrix WV, right, from the inputs, right? Uh, so um, let's erase this. Let's try to write things here. Uh, okay, so now what you do is you apply softmax, right? After you do softmax, um, or let's not write this. Let's assume that you did softmax and it's all normalized, right? So let's skip that part. So it has been done. Assume that it's been done, and after that you multiply it with the vector v, right? So when you do this, so what happens is you have some numbers, right? Q1, K1 transpose, and etc. But your value matrix V, right? Your value matrix V uh, is uh, is nothing but again it's V1, V2, etc. Vn. These are the value matrices or the vectors, value vectors of the same dimension, right? dV. In the paper, they say it's 64 dimensional vector, right? Right. So what's going to happen here is, as you can see, um, you're just going to do this. Um, you know, let's say you when you do matrix multiplication, what's going to happen is you're going to use these entries in the rows to do a linear combination of v1 till vn, right? So what's going to happen in the first, so the resultant matrix, right? The first row of that is nothing but q1 k1 transpose v1 plus q1 k2 transpose v2 plus etc. Q1 kn transpose vn, right? This is the first entry or the first row that will be created when you do the matrix multiplication, right? So this one, uh, as you can see, it's a linear combination of values, right? And it depends on the how close the query and keys are, right? If they are too close, right, if they are matching, then that particular value will be higher compared to the query and keys which are way too far away, right? So you can understand that this linear combination is basically trying to the linear combination is such that it somehow captures the information or captures the closeness of query and keys, and then based on that you're doing a linear combination of the values, right? So this is going to happen for every other row in the resultant matrix. So this matrix, if you create this matrix here. Okay, so what's going to happen is the same thing is going to happen for every other row. So you will have Q1, K1 transpose V1. I'm sorry, so it will be Q2 and plus Q2, K2 transpose V2 plus etc. plus Q2, Kn transpose Vn. So you're doing a linear combination of vectors based on this dot product values that you have in this particular matrix, right? So you keep going, and then the last vector will be Qn K1 transpose V1 plus Qn K2 transpose V2, etc., right? Qn Kn transpose Vn. So it's just a linear combination of values, right? Now the interesting thing is this is the output, right? This is the entire output of this function here, the attention mechanism, right? But the interesting thing is all this will be used. Um, so you can actually have a look at this. So here there's a residual connection, right? So basically your input will be used later to connect to, or basically added to the output of this attention mechanism, and then you do a norm, right? So that's exactly add and norm. So in add and norm, so here what's going to happen is um, you will have so they are applying a layer norm, right? I'll talk about layer norm later on. Layer norm of the input, right? The input, the embeddings that you pass, for each and every one of them, you're going to add the output, basically. So it's okay. So it's not exactly this matrix that will be added, because there are, as I said, it's multi-headed attention. So there are many heads, right, happening parallelly, right? Actually, there's h equal to eight of them happening parallelly, right? And so what's going to happen is at the end, it's going to be concatenated. All of them are going to be concatenated. The outputs of these matrices are going to be concatenated and then converted into vectors of dimension 512, because the embedding is dimension is 512, right? So you're going to add the output uh, to that, right? So I'm just going to denote it like this, right? So there's something, or let's do this. So let's say multiplied by h time, h is 8. So there's 8 times this process is happening, and then there's some concatenation going to happen, right? And then it will be converted back with a matrix W naught to a matrix whose you know of whose dimension is similar to the, or equal to the dimension of the input embedding, right? And then it will be added. So this is what is going to happen. So I will just denote it like this. So if we go down, right, if we just go down, this is exactly what they have mentioned here. Let's just scroll down and let's have a look at it. So there's this scalar dot product attention that we talked about, and then there's this multi-headed attention. So there are many attention heads happening in parallel, right? And then there's a concatenation happening, and then it will be passed on through a linear layer, and that's your output, right? So if you scroll down, so this is what is going to happen. So there's a multi-headed attention. The many heads, right? The output of many heads, where individual head is the attention on Q, K, and V, right? So this can be a little confusing if you're looking at this. So we said attention of Q, K, and V, so what's happening is here the Q, K, and V is coming from the previous layer, right? So maybe it's the input embeddings, or Q, K, and V from the previous layer. So as I said before, maybe this needs to be reminded. As you can see here, it's happening nx times. So it's not just one, there are many such layers, right? There are many layers after layer in the encoder part itself, right? So the output from the previous layer, right, will be used. So there are many layers in the encoder part itself. So the input from the previous layer, right, from which you will get your Q, K, and V, right? You will get your Q, K, and V from the previous layer, which will be further multiplied with the weight matrices and then on top of that, you will have your attention, right? So this is exactly, we don't need to get confused with this. so basically you can think about this as every time you get an output from the layer, right? Every time you get an output from this layer, right? Your vectors are of length 512, right? That's exactly what we did here, right? Um, right, so we can see here, so dimension is 512, and then that's going to be added to another 512 dimensional vector, right? And so there are many vectors, right? So it will be a matrix, right? But I'm talking about every row will have 512, it's getting added, and there's something called layer normalization happening. But know that it's 512, right? So if it's passed on to the next layer, right, we need to again reduce it back to a smaller dimension of dk and dv and dq, right? A smaller dimension of size 64. So you need to reduce it down, right? So you need to reduce it down. This is exactly what's happening here, right? The reduction, so 512 to smaller dimension, right? So that needs to be done before you do the attention. So that's exactly what they have mentioned it here. Attention q, so you multiply with the corresponding matrix, right? Whose weights will be learned, right? The parameters will be learned by the model. After that, you do attention. So this is the multi-headed attention, right? So you concat it at the end, you do again a weight matrix, right? Again, you do a weight matrix, which will bring your which will make your outputs again back to D model 512 length vectors, right? So that's the multi-headed attention. Now going back, let's right. So this is where we are. So some more details that needs to be mentioned is that so once you have the output, right? Once you have the output here of the vectors of length 512, it's just going to pass on to a feed-forward network, right? It's a normal feed-forward network that we all know about. With they use a ReLU activation. So there are two linear layers, right, with a ReLU activation in between, right? And again, there's a residual connection. So the input, right, it will be added to the output of this layer, and then there's this layer normalization happening. The same as this one. So there is layer norm, input plus whatever is the output that's coming from this feed forward network. And so let me show you the feed forward network. The equation for feed forward network. So it's exactly here. So you can see position wise feed forward network. See, it's two layers, right? Two linear transformations with ReLU in between, right? So ReLU is this maximum of 0 and the input, right? So here what's happening is a concatenation of two functions, right? So first, this inside one is going to happen. So xw1 plus b1. After that, you do a ReLU on top of that, right? ReLU is basically taking the maximum of 0 or this output of the first transformation, and then that is being concatenated to the next transformation, where basically this this maximum, right, whatever is the maximum, is will be multiplied with w2 plus b2, right? So it's concatenation that's going on. So it's this is the feed forward network, right? And to be a little bit more details, so dimension of the model is 512, but they say that the inner dimension, right? So one of this matrix W1 will have one of the dimensions 2048, right? So the dimension will be 2048, right? So that's some details. And going back, right? So that's encoder, right? I think we have mentioned everything here. Let me see if I missed anything, right? So there are many attention heads, right? At the end, you do concatenation, right? And then you multiply it with a matrix W so that you get vectors of length 512, right? And also you have a residual connection added norm, and then you have a feed-forward network as well, right? So this is the encoder part, right? It can look a little too much if you're just learning this for the first time. And if you're reading the paper for the first time, definitely this is going to be, you know, a lot of things going on, um, but yeah. So, anyways, let's look at now the decoder part. So the decoder part is exactly the same, uh, or not exactly the same, but it has similar components. Like you can see, there are three components here. One is the masked multi-headed attention. This is the normal multi-headed attention, and this is the feed-forward network, right? So what's the difference between masked and the multi-headed attention, right? So the difference here is that in masked, what will happen is if you create that matrix, right? So when you do QK transpose, right, divide by square root of dk, right? When you do this, you will have these entries here, right? Q1 K2 transpose and things like that, Q2 K1 transpose, Q2 K2 transpose, etc. Now, the thing is, this is your decoder part, right? And the idea is that you don't want your later tokens, all right, to really influence your previous one. So whatever inference that you're going to make for the first token, right, that you have given, right, whatever be the inference that you're going to make for the first token, it shouldn't influence from the later one. So because of that, what they do is they just try to kind of control this upper triangular matrix, right, by converting all of them to value called minus infinity, right? So this is even before softmax, right? So you don't do softmax before that. You just make it everything minus infinity, right? This is masking, right? After you do masking, then you do softmax, right? After that, you do softmax on this. Softmax. And this is the masked multi-headed attention. So it's exactly similar to this one, right? There are many things happening in parallel, H8, right? Many of them are happening in parallel. Same thing, but the only thing is they do this masking process because you don't want the later tokens to have an influence on the previous ones, right? All right, so that's what happens here. And let's go further. And the reason for making it into minus infinity is because softmax, when you apply it to minus infinity, right, e to the power minus infinity is 0, right? So that's the idea behind converting it into a very large negative number, basically minus infinity, right? So in the limit, it just goes to 0. So you convert the value to that. Okay, so now interesting thing here is that you have two connections coming from the encoder, one connection coming from the previous layer of the decoder part, right? So what happens here is that you will have keys and values coming from the previous encoder, right? And then you will have queries coming from the encoder part, right? The previous layer in the encoder part. Now this is clear, right? So you have this keys and values from the encoder. Now the encoder is kind of the decoder is using its query to find the relationship, or kind of um, you know trying to extract some similarity from the outputs from the encoder part, right? So so it has these three connections, K, V, and Q, and then the rest of the process is the same. So it's multi-headed attention, right? It's the same thing as we discussed here. There's also residual connection, right? There's always residual connection, right? It's kind of like whatever be the input, you're adding on top of that some small changes, right? And by doing it, you're kind of learning you're kind of changing the embeddings of these vectors to align itself based on the context, right? Based on the meaning of the entire sentence, right? That's exactly what's going on when you do this residual connection, right? Or possibly one of those outcomes of this process is that, right? So you're tweaking the embeddings. And also this final thing, feed-forward network, it's the same as this one, right? Two transformations, ReLU in between, right? And then you have layer normalization, right? So yeah, that's it. I think the only thing that's left is this last part. You have a linear layer and then a softmax layer, right? So this is basically used to output probabilities, right, of your vocabulary, right? And based on that, what is the word with the largest probability, right? Uh, it will pick that, right? It will pick that, and then or there can be many ways of selecting the output words, right? Output tokens. Either you can do it randomly, or the probability with or the word or the token with the largest probability and things like that. But so this part is clear. So there's a linear part and then there's a softmax. All right. So now this model is auto-regressive. That means whatever be the output, right? So this is output one. You're going to cycle it back, and then you're going to add it to the previous token, which was passed on. So it's the start token plus output one, and then this whole thing is going to pass through the network, right? And then it will produce a new output two, which will be added on to the previous one, and then it will pass on through the network, right? So this is happening, um, like this is the autoregressive part of the model, right? Okay. Again, I should mention this is nx, so this is happening many times, so 6 times here, right? As mentioned in the paper. And yeah, so I think this is the encoder and the decoder part, and I've mentioned all the details. Right, so this is the entire transformer architecture in nutshell. Okay, so it can be a little too much when you're just looking at this whole thing. If you're when you're trying to understand the entire small bits and part of it, right? There can be a lot of things going on, but once you get a feel of everything, things are going to be better. Let's scroll down and let's have a look at the rest of the paper. So here it's about encoder and decoder, right? So I think we have discussed all of this. So they use layer normalization, and they use 6 of them, right? 6 layers, 6 stacks. So your n is 6 here, and then so the model dimension is 512 that we have already discussed before. You have a decoder in 6. So yeah, this is exactly what we discussed. We also modified the self-attention sublayer in the decoder stack to prevent positions from attending to subsequent positions, right? Right, so this is exactly what we did, the masking procedure. And then you have the attention mechanism. We have discussed this in detail. So all these things we have mentioned the application of attention in our model. Say so they use encoder decoder attention. So we have seen this the way we connect encoder to decoder, right? Um, and encoder contains self-attention layers, which we have mentioned. In the decoder, we use masking, right? That we have also mentioned. And they have discussed this feed-forward network. All right, so that's good. So yeah, similar to other sequence transduction models, we use learned embeddings um, to convert the input tokens and output tokens to vectors of dimensions D model, right? Um, right. So they use these input and output tokens to this dimension D model, right? So they convert it into D model. Um, so we also used learned linear transformation and softmax function to convert decoder output to predict next probabilities, right? So they are using a learned linear transformation and a softmax function um, to convert the decoder output to predict next probabilities. Um, so we share the same matrix. Yeah, so some details here. And they have something here. So this is in embedding layers, we multiply those weights with root dk, root square root of d model, right? So this is another thing that they do in the embedding layer. They do multiply it with square root of dk, right? Um, there's just another thing that they do here. Um, right. So, and um, then what they have here. So the rest of the paper is about some more informations like the positional encoding, how you do positional encoding for the input tokens, right? So they, as I said before, they use sine and cosine function. And what you have is here they have given a nice little table saying, depending on the layer type, what's the complexity per layer, sequential operations, and maximum path length, right? So in your self attention, uh, your sequence, let's say it's of length n, then the complexity is n squared times d, right? Because you attend to every one of those possible combinations of sentences, and then you do a dot product of two vectors of size d, right? So you do this n squared times d, right? So your order is that, right, for individual self attention. And the sequential operation is one, so you don't need to do any sequential process here, right? So in self attention, what happens is every word is so you are allowed to find relationship between one word and the other word in the same sequence in the same sentence, right? So your operation sequential operation is just order of one. Maximum path length is also order of one, right? But then when you have recurrence, right, you have this order of n as a sequential operation and the max path length. So because you have to attend to all those n um, words to be able to yeah, so because you process one token at a time sequentially, right? So this give rise to order of n here. And for the rest of the layer types, you have the corresponding complexity and the sequential operation and the max length, right? Things like that. Um, and so they have some reasons for why self-attention is needed. And then they describe the training process and the hardware and the optimizer that they used and regularization and the results. Um, Right. So and a little bit more, right? So what I will do is I'll just wind up for this particular video here. And for the next one, I'm going to start from here and describe the rest, right? If there's something informative, if there's some interesting thing in the paper, I will just go through it, right? And just point it out, right? Specifically, I will discuss why self-attention, right? So why do you need self-attention? Um, yeah. So I think that's good. So we'll wind up here. Hope you like this. If there is any clarity or if there is anything that you want to point out in my explanation, just please feel free to put that in the comment section and I will be very happy to look at it. Yeah, so that's it. So thank you so much for sticking with me till here. I will see you in the next video. Till then, take care. Bye.